Okay. So gravity's acting. What else? Normal force. Yeah, we got a normal force acting.
I don't want to hear my voice about coding. I'm just getting into it.
Yeah.
What was we talking about?
American Idol. I was watching the movie.
She was talking about American Idol
Oh.
instead of paying attention.
Oh, that's right. Okay, so there's our normal force. Okay. So now I've got a question for you. This is kind of tricky. I want you to see this. Which of those two forces is providing the centripetal acceleration to make this thing go in a circle?
Normal.
Yeah, it is the normal force, isn't it? Okay, and keep in mind that, we mentioned this yesterday, centripetal force is not like, it's not a, it's not a, what's the word I'm looking for? Agent. It's not the agent of causing something,
Like when?
the agent of the change. It's not, it's just a category. It's like, and literally what we're going to see is centripetal force literally just means the net force acting towards the center of circular motion. That's really all it means, right? It can be provided by other things, other agents. There are agents of the centripetal force. Could be friction, could be gravity, could be tension, right? Okay. So this looks an awful lot like the problems we dealt with in previous chapters when we were looking at an object sliding down a hill, right? If this puck were just sliding down the ramp, it had no circular motion at all, which of the two forces, normal force or gravity, would be causing it to slide?
Gravity.
Gravity would, right? Because the gravity has a component. If I break gravity up into components, it has a perpendicular component, but more importantly, it has a parallel component that would accelerate the puck down the curve, or down the ramp, right? Okay. Normal force does not. Normal force is completely perpendicular, so it cannot have a parallel component because they're at right angles, right? Okay, but this is a different situation, isn't it? In this situation, the puck is traveling around the track in uniform circular motion, and so the centripetal force would be acting in what direction? Is the centripetal force acting exhibit A? Is it acting in that direction, or is it acting in that direction?
That direction.
Second one, right? It's pointing towards the center of the circle, right? So it's not acting down the track, it's acting horizontally towards the center of the circle in this particular frame of the movie, right? So for the centripetal force, which one of those two vectors is providing a component? The normal force, right? It's the normal force, it's not the gravity. The gravity does nothing to push the puck towards the middle of the circle. It's the normal force that does, right?
But doesn't the gravity still have a parallel component?
No, it doesn't. The gravity only has a perpendicular, only has a y component. It has no horizontal component at all, right? And does that make sense that a vector can never have a component perpendicular to itself, right? One way to visualize components is with shadows, and that's a good way to think about it. Like, let me illustrate that for just a second. So let's say that we've got, here's the road or the x-axis. You decide what you want it to be. Here is a vector or an arrow sticking out of the road. You decide what you want it to be. If the sun is directly overhead, so the light is coming down vertically, would you agree that this is the shadow cast by the vector? Okay, that's also what we would call, if this is vector v, then this is what we would call v sub x, right? Okay, now, but what happens if the vector is perpendicular to the pavement, or the arrow is perpendicular to the pavement? Does the arrow cast a shadow? No, so there can be no x component of a vertical vector. Make sense? Okay? All right, so then what we need to do is we need to break up the normal force into components, right? We need to break the normal force up into a y component and what we might call a centripetal component. Okay? And if we redo this free body diagram, orthogonalize, right? If we put in just the components instead of the vectors, so we're essentially just doing this. We're going to trade this orange normal force for the red components. Okay? Then we end up with, here's our free body diagram, right? Whoops. Okay, now let's call this angle theta. So which angle up here in this triangle, given that this is a right angle, which of those angles is going to be theta? Bottom one, right? And we can see that a little bit because that's the acute angle and that's the obtuse one. But wouldn't you agree that if I were to, and you got to kind of play these movies in your head, if you practice this, you get better at it, and this is really helpful. If I were to hinge this thing, what if I were to drag this piece down? If I drag this piece down, wouldn't that make the normal force more vertical? You see that? So the two angles that would behave the same then, as this pink angle got smaller, whoops, wouldn't this angle get correspondingly smaller? Right? So they must go together, huh? Right? So those must be the ones that are congruent. It's just kind of a little trick. Does that help? So that's theta, that's theta. So then what am I going to call this vector? It's supposed to be red, but that's going to be my y component. That's normal force times what?
Say that again?
Cosine?
Cosine, isn't it? It's normal force times cosine theta. That's the vertical component, right? And then the horizontal or the centripetal component would be normal force times sine theta, right? And so just like we always do, now we can set up our equations of motion, right? So we're going to break this thing up into vertical, an equation that describes the vertical forces and an equation that describes the centripetal forces. So vertically, the y component of net force equals what? What are the components or vectors that add up vertically?
So that's cosine, cosine theta.
Okay, so the positive one would be normal force times cosine theta minus mg. And what's that going to equal?
0.
0, yeah, because there is no movement vertically. The puck stays the same height the whole time, right? So there's equation 1. What stuff, let's go ahead and let's circle in red anything that's unknown in this problem, in that equation.
FN.
The normal force is, isn't it?
You don't know what mass is.
And we don't know the mass either, so I'll go ahead and circle that too. Let's go down to the other equation. So if we look, now instead of calling this net force centripetally, isn't that really just the same thing as centripetal force? Right? So do you see the centripetal force really is a net force? It's a net force in the centripetal direction. That's what we mean by centripetal force. Okay, so centripetal force equals, there's only one vector, right? It's all, the only contributor centripetally is normal force sine theta, right? And that must equal what? So centripetal force equals mass times centripetal acceleration, right? So we know that's always true. Centripetal force equals mass times centripetal acceleration, but what's centripetal acceleration?
V squared over R.
V squared over R. Right? That's the form of the centripetal acceleration equation we'd want here because we're dealing with radius and speed, right? And that's what we're working with in our problem. So then this just becomes m v squared over r, right? So once again, what is it that's unknown here?
Mass.
Okay, mass,
V.
V, which is what we're looking for, and normal force, right?
So a lot of missing pieces.
It's a lot of missing pieces, right? Okay, but look at this. These two appear, they both appear in the two equations of motion, and so we ought to be able to isolate, substitute, right? Solve for normal force in one of the equations and substitute into the other. Well, we're going to want to substitute probably into the bottom one because we're really ultimately trying to find the speed, aren't we? Right? So in the top equation, if we solve for normal force,
MG.
what are we going to get? So let's label these. This is equation 1. Whoops, that's equation 2. So equation 1 is going to become, if I solve for normal force equals mg divided by cosine theta. I'm not going to keep color coding these. That's just going to be old. So that's a substitution equation, right? We can substitute that into equation 2. And then what does equation 2 become? So normal force we're going to replace with this, right? So we get mg over cosine theta times sine theta, right, equals mv squared over r. Okay, but look what happened to my m's.
They can't.
They cancel, so we lucked out, right? We were able to cancel out one of the unknowns, and that's the physics god's way of telling us what?
We can do this.
What's that? What's the physics gods are telling us something really profound about this situation? Doesn't matter, right? It's independent of mass. Good.
Victoria,
Yeah.
just really quick, so we're going over this stuff in trig right now, and this is
Yeah.
sine over
What's it equal?
tangent.
Tangent. There you go. Perfect. Okay. Now this isn't for people who are not in trig. It's not like it's absolutely essential that you even do that, because you could just take the sine of the angle on your calculator divided by the cosine. But it's a lot easier if you can combine it into one trig function. And so you're right. In trig, we know that tangent theta is defined as sine theta over cosine theta, right? So then look what we could do. We could m times g times sine theta divided by cosine theta is the very same thing as mg tangent theta. And then it's just one thing to do on your calculator instead of two, right? And that equals v squared over r. So what are the two steps in order to get to v?
I'm in there, so.
Get that out of there.
Oh, whoops, you're right. No m.
We don't want it.
It's gone. So what are the two steps in order then to get the v by itself? First we
Multiply by r.
multiply by r, both sides, and then
Square root.
square root. So would everybody agree if I do those two things, I'm going to get v equals gr tangent theta, or rg tangent theta, makes no difference, square rooted,
Yep.
right?
How about that?
How about that? And all this stuff we know. We know the radius. The radius of the track is, what, 63.3 meters? The angle is 5.14 degrees. That's all stuff we can put in our calculator.
Woo.
Isn't that cool? So let me ask you this then. Does that make sense? Should this, let's look at those things. This answer is telling us that as r increases, the necessary speed should increase. Makes sense, doesn't it? Wouldn't you agree that if this track, the radius of the track increased and the curvature were smaller, I would have to go a lot faster to be able to stay up on the track? Doesn't that make sense? If it were a really tight turn, I wouldn't have to go very fast to stay up high on the track, right? Our intuition probably tells us that. How about the angle? Well, yeah. If the angle gets steeper, then there's a much bigger tendency to fall off the track, and so I have to go faster, right? To compensate for that.
Yeah.
Okay. And then what about gravity? If we were on a planet where gravity were much, much stronger, that would tend to pull this puck down the track much more forcefully, and so I'd have to go much faster to counteract that, right?
Yeah.
So it seems to make sense. The physics god steered us right. Okay? All right.
Go to band.
Oh, go. Go. All right, have at it. You guys can work.